Hey, welcome back. In this video, we're going to focus on prime numbers, and we'll also discuss greatest common divisors and least common multiples. We've seen some information about prime numbers in past videos. For example, in the video that I posted on strong induction. This video, though, we're going to do a lot more with prime numbers. So first, let's start with the definition. What does it mean to be a prime number? We say that an integer p greater than 1 is prime if and only if it has the following property. And this property is that the only positive integer divisors of p are 1 and p. Here's a list of the first few prime numbers. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, and so on. If we have some integer n greater than 1, which is not prime, we call n composite. And in the strong induction video, where we talked about primes before, we proved in that video, using strong induction, that every integer n greater than 1 is a prime or a product of primes. Now, we're going to prove a very well-known fact about the prime numbers. And that is the fact that there are infinitely many primes. In order to prove this, we can use a proof by contradiction. So, we will suppose for contradiction that there are only finitely many primes. And we'll try to use this to derive a contradiction, and that will imply that there must be infinitely many primes. So based on our assumption here that there are only finitely many primes, if there are only finitely many of them, then we can list them in order from least to greatest. So we'll list them as P1, P2, P3, all the way up to P sub k for some finite k, where P1 equals 2, P2 equals 3, P3 equals 5, P4 equals 7, and so on. We will define this integer, n, to be the product from I equals 1 to k of P sub I. So the product of all of these primes. And then plus 1. So this notation, if it is somewhat unfamiliar, let me also write it in a form that might be more familiar. So an equivalent way to write this is n equals P1, P2, P3, up to P sub k. We'll put some parentheses around this so it's clear that it's separate from this plus 1. So that product plus 1. So same thing, written in two different ways there. Now, this number n, this integer n that we just defined, it is an integer because it is a product of integers plus 1. That must be an integer. N must have some prime divisor because we showed in that strong induction video that every integer n greater than 1 must be a prime or a product of primes. And if you're a prime, then the prime divisor is the integer. And if you're a product of primes, then you can pick one of those primes in the product as the prime divisor. So that tells us n, since n is greater than 1, it must have some prime divisor. However, n is not divisible by any of the primes on our list, P1, P2, up to Pk. Why is that? Because n mod P sub I equals 1 for all 1 less than or equal to I less than or equal to k. So we can see if n mod P sub I equals 1, that means that n is 1 more than a multiple of P sub I for each I. And if n is 1 more than a multiple of P sub I, then n cannot be a multiple of P sub I, because P sub I is not 1 for any I. So these last two bullets, tell us that n must have some prime divisor, but this prime divisor does not appear on the list right here. And that's bad. That's a contradiction because we assume that all of the primes were on that list. So that tells us, since we just got a contradiction, that there had to have been infinitely many primes because our assumption that there were only finitely many primes gave us the contradiction. So that's the proof. And we can see another simple fact, this time about composite numbers instead of prime numbers, but it's a fact involving prime divisors of composite numbers. So just to review the definition that we saw on the earlier slide, the integer n greater than 1 is called composite if n is not prime. And if n is not prime, that means that n must have some positive integer divisor besides 1 or itself. So if n is composite, then we have some positive integer divisor. We'll call it m besides 1 or n. And here's a claim that we're going to prove. We're going to prove that n must have some prime divisor, we'll say p, which is less than or equal to the square root of n. And in order to prove this, we're going to use this positive integer divisor besides 1 or n, and we'll call it m. So m is the positive integer divisor of n, such that m does not equal 1 and m does not equal n. And I said I really mean a. M is a positive integer divisor of n, such that m does not equal 1 and m does not equal n. Because it's possible there might be multiple positive integer divisors of n besides 1 or n. So we'll just pick one of them that has this property. And we know there's at least one because, again, n is composite. So given this m, since we know that m is a positive integer divisor of n, and m is not equal to 1 or n, then n over m is an integer. And we know that m is less than or equal to square root of n, or n over m is less than or equal to square root of n. And this might seem confusing right here. Why is this true? So we'll explain that. Also, I want to note, besides the fact that this is an integer, we also know that n over m does not equal 1, and n over m does not equal n. And this is because m does not equal 1, and m does not equal n. So m is not equal to 1, and m is not equal to n. And that tells us then that n over m does not equal n, and it does not equal 1. So n over m is an integer not equal to n or 1. And I claim this right here must be true. And we can see why that is true. And that one is a real proof, a real quick proof by contradiction. And if we did have this false, so if m less than or equal to square root of n, or n over m less than or equal to square root of n, if this was false, we would get the contradiction right here. So if false, we would have this contradiction that n equals n over m times m. That's just by definition right there. N over m times m, the m's cancel, will give you n. But if we had that this was false right here, if that was false, it would mean that m is greater than the square root of n, and n over m is greater than the square root of n, if that's false. So if it's false, we would have n over m times m right here is greater than the square root of n times the square root of n. In other words, the square root of n squared. And that gives us n. So we would have n strictly greater than n, which would be a contradiction. So that's how we know that at least one of m, or n over m, is less than or equal to the square root of n. So we can break our proof into cases now. So if m is less than or equal to the square root of n, then the least prime divisor p of m is going to be a prime divisor of n. And since m is less than or equal to the square root of n, that means that p is also less than or equal to the square root of n. So that p is the prime divisor of n that we're looking for in that case. In the other case, if we have n over m is less than or equal to the square root of n, then we can take the least prime divisor p of n over m. And we know that if p is a divisor of n over m, then we have to have p less than or equal to the square root of n, because n over m is less than or equal to the square root of n. And if p is a prime divisor of n over m, then p must also be a prime divisor of n, because n over m divides n. And again, I want to note here, what we're using is that n over m does not equal 1, and n over m does not equal n here. So the fact that n over m does not equal 1, we can find a least prime divisor p of n over m. Because if n over m was equal to 1, then it wouldn't have any prime divisors. But we know that every integer greater than 1 has prime divisors, because it's either a prime or it can be written as a product of primes. So that completes what we're trying to prove here, that n must have some prime divisor p less than or equal to the square root of n, because we showed in either of these cases we can find a prime divisor p of n with p less than or equal to the square root of n. And we showed that one of these cases must always be true, at least. So it's possible for both of them to be true at the same time, but at least one of them must be true. So we show in either case we get the prime divisor we're looking for. And that completes the proof. So this was just a proof by cases. And there was a little bit of a proof by contradiction on that bullet. So now we can go on to defining the greatest common divisor. You've probably seen this before. You probably have calculated it back in school. So the greatest common divisor of the integers x and y is just the greatest integer that divides both x and y. And we use this notation to write it GCD of x comma y. And we can look at some examples here. So GCD of 4 comma 10. We want to find the greatest integer that divides both 4 and 10. So we can see that 1 divides them both, but also we see that 2 divides them both. And if you check, you see that that is the greatest integer that divides them both. So the answer is 2. GCD of 10 and 35. Again, we can see that 1 divides them both. Then we start counting up, and 2 does not divide them, 3 does not divide them. 2 divides 10, but it doesn't divide 35. 3 doesn't divide either of them. 4 doesn't divide either of them. 5 divides them both. And if you check higher than 5, you see that nothing else divides them both. So this one's 5. GCD of 60 and 144. So this one, we can check 1, we see that divides them both. 2 also divides them both. So does 3. And so does 4. 4 divides them both. 5 does not divide them both. 6 divides them both. 7 does not. 8 divides one of them, but not the other. So 8 does not divide 60. 9 divides the 144, but not the 60. 10 divides 60, but not the 144. 11 doesn't divide either of them. And let's see, 12. 12 divides both of them. So 12 divides 60, it's 12 times 5. 12 divides 144, it's 12 squared. And that is the greatest common divisor of those two. So there's no integer greater than 12, which divides both of them. And here's the last one, GCD of 90 and 121. We see that 1 divides them both. And if you check any integer higher than 1, you see that it doesn't work. It doesn't divide them both. So the answer is 1 for that. If you have two integers x and y for which the GCD of x and y is 1, we say that x and y are relatively prime. For example, 6 and 85 are relatively prime. They have no common factors. 20 and 21 are also relatively prime. So the greatest common divisor of both of these pairs, 685, and the pair 2021, we get GCD of 1 for both those pairs. In fact, you can generalize that last one. If you take an integer x, and you take the GCD of x and x plus 1, you always get 1. So x and x plus 1 are always relatively prime for integers x. And 20 and 22 are not relatively prime. So they're both divisible by 2. So the GCD is greater than 1. It is 2 in that case. So we're going to talk about some methods for finding the GCD. First method is prime factorization. This method works pretty well when you're working with small numbers that are easy to factor. So we have our numbers x and y. We'll write the prime factorization of x. We can write it as x equals p1 to the e1, p2 to the e2, all the way up to some pk to the ek. We'll also write the prime factorization of y. We'll use the same primes in the factorization for y, but different exponents. So if there's some prime which does not appear in the prime factorization of y, but it does appear in the prime factorization of x, then we'll use an exponent of 0 for that prime in y. Similarly, we'll do the same thing for x if there's some prime which appears in the factorization for y but not x. So if we have these two prime factorizations, x equals pi to the ei multiplied from I equals 1 to k, y equals pi to the fi multiplied for I equals 1 to k, then the GCD of x and y is going to be equal to p1 to the minimum of e1 and f1 times p2 to the minimum of e2 and f2, all the way up to pk to the minimum of ek and fk. We can see that that quantity in the last bullet definitely divides both x and y, because the exponents of each of the primes, p1, p2, up to pk, all these exponents are less than or equal to the exponents of the primes in x and in y, because we're taking the minimum. So it has to divide x and y. We also see that if we increase any of those exponents, it will no longer divide at least one of x or y. And it's possible it'll no longer divide both of them, but it will no longer divide at least one of them. And that will mean then that it will no longer be a common divisor of x and y. So this formula actually makes sense because it's giving us a divisor. It clearly divides x and y because the minimum of e1 and f1 is less than or equal to both e1 and f1. And the minimum of ei and fi in general is less than or equal to both ei and fi. So it's definitely a divisor, and it's also the greatest divisor because if you increase any of the exponents, it's no longer a divisor of both of them. So that is the greatest common divisor. And we can use this formula to find some GCDs pretty easily. So here's an example. But I just want to mention what I said before, which is that this formula works pretty well when you're working with small numbers that are easy to factor. When you're working with numbers that are not easy to factor, then there's a much better algorithm for finding the GCD. So let's look at this example though, 60 and 128. We can factor these. 60 first we'll factor as 2 squared times 3 times 5. We'll write that as 2 squared times 3 to the 1 times 5 to the 1. 128, we'll factor this as 2 to the 7. So it's a power of 2. But since the 60 had 3's and 5's in the prime factorization, we'll also include a 3 to the 0 and a 5 to the 0 in the prime factorization for 128. Now we can apply our formula. GCD of 60, 128, we get 2 to the minimum of 2 and 7 times 3 to the minimum of 1 and 0 times 5 to the minimum of 1 and 0. That gives us 2 squared times 3 to the 0 times 5 to the 0, and that gives us 4. And that's the GCD of 60 and 128. Now here's the faster way to do it. It's called the Euclidean algorithm. And I actually made a video that goes over this algorithm in full detail, and it also covers some other related algorithms. The video is called Decrease and Conquer 1. and I posted it in the playlist so you can find it pretty easily. Now let's move on to the least common multiple. The least common multiple of positive integers x and y is the least positive integer that is divisible by both x and y. And here's the notation for it. We denote it LCM of x comma y. So here's some examples. LCM of 4 and 10. We want to find the least positive integer that's divisible by both 4 and 10. So we can think of some multiples of 4, like 4, 8, 12, 16, 20. We can think of multiples of 10, 10 and 20. We just said 20 twice, and that was the smallest one. So that's the least common multiple. It's 20. LCM of 10 and 35. Let's list the multiples of 10. 10, 20, 30, 40, 50, 60, 70, 80. Let's list the multiples of 35. 35, 70, 105. We said 70 twice. That's got to be it. It's 70. Yep, least common multiple. LCM of 60 and 144. So here we can list the multiples of 60. 60, 120, 180, 240, 300, 360, 420, 480, 540, 600, 660, 720, 780, 840, 900, and so on. Now we can list some multiples of 144. So we get 144, we get 288, and the next one is going to be 144 times 3. So we get 432. Then we get 576. And then the next one is going to be 576 plus 144. That gives us 720. That's one that we said for the list of the 60 multiples. 720 was on both lists. So we get 720 as the LCM of those two. There's a better way to calculate the LCM, so we'll talk about that. But one more example before we get to that. The LCM of 5 and 7. We can see that this one, if we list the multiples here, multiples of 5, we get 5, 10, 15, 20, 25, 30, 35, 40. Multiples of 7, we have 7, 14, 21, 28, 35, 42, 49, and so on. And there's one that we just said twice. It occurred on both lists. It was 35. What's interesting here is that we saw that the LCM of 5 and 7 was equal to 5 times 7. In general, if we have positive integers x and y, which are relatively prime, then their LCM is equal to their product. So now let's talk about some techniques for finding the LCM. So method 1 is going to look similar to the first method that we saw for finding the GCD. And this is prime factorization. So same setup with the x and y. X equals the product of pi to the ei for I equals 1 to k. Y is the product of pi to the fi for I equals 1 to k. And we can calculate the LCM of x and y as the product of pi to the maximum of ei and fi for I equals 1 to k. And we can see that this makes sense for two reasons. We can see that it's divisible by both x and y, and that's because all of the exponents here, all of them are maxes. All of those maxes are at least the corresponding exponents in x and y. Max of ei and fi is at least both ei and fi. So that is why the quantity on the right must be divisible by both x and y, because all of its prime exponents are at least the prime exponents in both x and y. On the other hand, if we decrease any of the exponents, then it will no longer be divisible by at least one of x or y. So if we bring any of these exponents down, any of the maxes down by 1 or more, then one of the exponents for x or y is going to be greater than the exponent that we have on the right if we decrease any of these maximums. And so that will mean that the quantity on the right will no longer be divisible by either x or y, or possibly both of them if they both have the same exponent for that prime. So that tells us that this quantity on the right, since it's divisible by x and y, that gives us the first part of the definition of LCM. So it has to be a multiple of both x and y. And then the second part of the definition has to be the least common multiple. So if we decrease any of those exponents, if we make any of the exponents smaller, then it's no longer a multiple of both x and y. So it is a multiple of both of them, but if we decrease it at all, then it's no longer a multiple of both of them. Thus, that gives us the least common multiple. And we can use this formula for the same numbers that we saw with the GCD example. Let's say we want to do the LCM of 60 and 128. 60 we can write as 2 squared times 3 to the 1 times 5 to the 1. 128, we're writing that again as 2 to the 7 times 3 to the 0 times 5 to the 0. And so the LCM of 60 and 128 is going to be 2 to the maximum of 2 and 7 times 3 to the maximum of 1 and 0 times 5 to the maximum of 1 and 0. So we get 2 to the 7 times 3 to the 1 times 5 to the 1, and this simplifies to 1920. And there's one other method I'll mention for finding the LCM. And this is a really fast method if you already know the GCD. So let's say you calculated the GCD using maybe the Euclidean algorithm, because that will be faster than the other algorithm we saw when we're considering large numbers that are not necessarily easy to factor. So we have some way of finding the GCD, maybe the Euclidean algorithm, maybe some other method, maybe something even faster. So suppose that we know the GCD already. Well, we saw these formulas on the previous slides, these formulas in terms of the prime factorizations. If we have x equals the product of pi to the ei for I equals 1 to k, and y equals the product of pi to the fi for I equals 1 to k, then we saw the formula for GCD was the product of pi to the minimum of ei and fi for I equals 1 to k. And the formula for LCM was the product of pi to the maximum of ei and fi for I equals 1 to k. And if we multiply these two quantities together, let's see what happens. We get GCD of xy times LCM of xy. So we get pi to the minimum of ei and fi plus the maximum of ei and fi. And I'm going to write something here, an interesting fact. Minimum of AB plus maximum of A and B. This equals A plus B. You can think about it for a second and see why that's clearly true. And that's what we're using here to get this. So GCD of xy times LCM of xy is the product of pi to the minimum of ei and fi plus the maximum of ei and fi for I equals 1 to k. And that sum of the minimum plus the maximum is just ei plus fi. So we get the product of pi to the ei plus fi for I equals 1 to k. And that's exactly what we have right here. And we can see that that quantity, the product pi to the ei plus fi for I equals 1 to k, this is equal to P1 to the E1, P2 to the E2, all the way up to PK to the EK. And we can multiply it times P1 to the F1, P2 to the F2, all the way up to PK to the FK. So all I did here is I split these sums up. I wrote P1 to the E1 plus F1 as P1 to the E1 times P1 to the F1. Same with the P2 to the E2 plus F2. I did the same thing there. P2 to the E2 times P2 to the F2. Now notice this quantity here, that's just my X. This quantity here, that's just my Y. That's how I got X times Y right there. So this gives us a real simple formula to evaluate the LCM. And I'll erase some of my marks here so we can read that. So our formula is LCM of xy equals x times y divided by the GCD of xy. So all we did is we took this previous bullet right here and we divided both sides by the GCD. So if we want to find the LCM of x and y, all we have to do is multiply x times y and divide by their GCD. So that gives us a real fast way to find the LCM if we already know the GCD, because multiplying x and y, this is pretty fast to do. And so if you use the Euclidean algorithm, which I go over in the other video that I post this week, you can find the GCD using the Euclidean algorithm for any integers x and y. And then you can just plug it in to this formula to find the LCM of x and y. So this gives us a pretty fast way to find both the GCD and the LCM. If you use the Euclidean algorithm to find the GCD, and then you use this formula for the LCM. And that's everything for this video. So thanks for watching.